from yesterday's lecture, the Hilbert system, changing the terminology to soundness rather than consistency, so that we reserve consistency for a set of sentences, and we think of a proof system as being sound, and which is a fairly well known, which is a fairly well used word for proof systems in general. So might as well use that. So we are talking, and of course, the main reason for that is that it's possible to prove inconsistent things if your set of assumptions is inconsistent. So the soundness of a theory does not necessarily mean you can't prove any inconsistencies, right? So if you make an inconsistent set of assumptions, you can actually prove inconsistent things, which is fine. That's why it's important to define the soundness as being one in which you cannot prove all possible sentences. I mean, or rather, not all possible sentences are theorems, formal theorems. So that means, given an empty set of assumptions, whatever you can prove should not be the entire language itself. Right? So that's the notion of soundness of a formal theory, and let's quickly go through it. So basically, we showed that every instance of every axiom schema in the Hilbert system is a tautology, and the modus ponens rule actually preserves the property of tautologousness, right, of tautologies, right? So, since we know that not all formulae in the language L0 are tautologies, it therefore shows that the Hilbert system is sound.
Right. So as I said, the proof of soundness it just means that showing each of the axiom schemas actually is a kind of a template for a class of tautologies following a certain pattern, right? And the proof that modus ponens preserves tautologousness is also something that is easily done. So, and from the soundness of the Hilbert system, we also get that every formal theorem, that means every statement that you can prove without any assumptions is a tautology, and therefore, the system is sound. And now, let us actually look at the completeness. So, what I said was, so one thing is that the only formal theorems of the system are tautologies, and but we need for completeness we need to show that every tautology is in fact provable in the system, right. So, and then a consequence of that is that if the Hilbert system is complete, then by this exercise in which you derive the axiom schemas Ks, S and N in the Gentzen system, it follows that the Gentzen system is also complete, right. And what I said was we were yesterday we were actually looking at simulating the truth table, and in that proof of the simulation of the truth table there were quite a few errors. So, the first thing I thought I would do is correct those errors, and the next thing I thought was I will actually go through the proof of completeness because it is non-trivial. So we will simulate a truth table. So, the truth table lemma, as I call it, essentially says that you take for any formula with whose atoms are contained in this set, in some finite set P1 to Pk, for every truth assignment tau, there is a formal deduction from the assumptions Pi star, the formula phi star, where Pi star and phi star are defined as being Pi and phi if the truth assignment tau gives them the truth value 1, otherwise the negation of Pi and phi. Yeah. Okay. So, this so as I said, so we are going to this proof is by induction on the number n of operators in the formula phi. So, and the set of assumptions is the set gamma, which is, so essentially we are taking some particular row of the truth table and P1 star to Pk star are the set of assumptions. If the number of operators in phi is 0, then phi must be an atom, and therefore, it trivially follows that P1 star is syntactically the same as phi star, and therefore, and that is provable, right. I mean, that is part of the monotonicity considerations, and that is provable. And anyway, you can prove p arrow p without any assumptions, and then by the deduction theorem you can move the left p to the assumption, and therefore you have proved this. Okay, so assume this induction hypothesis that for all the claim holds for all well formed formulas of which have less than n operators, and we take this induction step. So, the induction step of course is by case analysis on the structure of the formula. So, let us assume that phi is a formula with n operators, and then we have two cases to consider essentially. One is where phi is of the form not of some psi, where psi has less than n operators, and the other case is when phi is of the form some psi arrow chi, where each of psi and chi has less than n operators, right. Okay. So, the case when phi is not psi, then we by the induction hypothesis we actually have a proof tree T1 where from the assumptions gamma you can actually prove psi star, whatever that is. Yeah. Okay. So, then of course, then you have two sub cases. One is whether the truth assignment to psi is 1 or 0. So, in each case what happens is if the truth assignment to psi is 1, then phi must be 0 because phi is not psi, and therefore, psi star is the same as psi and phi star is not phi, which is the same as not of psi. And then this deduction essentially shows that from gamma you can prove phi star. Yeah. So, this proof tree essentially shows this. Okay, given that so we actually had gamma proves psi star, but I have written gamma proves psi here because we know psi star is the same as psi, right. Okay. In the case when psi is been assigned 0 by the assigned false by the truth assignment, then T of phi must be true, I mean phi must be true. Therefore, psi star is not psi and phi star is the same as phi. So, it is also not psi. Okay. So, by the induction hypothesis we have this, and the proof is clear. In the case when phi is of the form psi arrow chi, we have essentially three sub cases. When psi is assigned false, clearly it does not matter what chi is. When chi is assigned true, clearly it does not matter what psi is. The only other case, the third case, is when psi is assigned false and chi is assigned true. I am sorry, when psi is assigned true and chi is assigned false, and that is the important case. So, in each of these cases, so in the case when psi is assigned false and it does not matter what chi is, we have psi star is not psi. So, that means our induction hypothesis says that there is a proof tree T1 of this form, and phi must therefore be true, which means phi star is the same as phi, which must be syntactically psi arrow chi. So, now we then have this proof tree. This is one of the exercises. Yeah, you can see. So, you can prove not x arrow y, right. So, that, and you can actually apply this this derived inference rule, and you can claim that from gamma you have proved not psi arrow chi, and you already have not psi here by modus ponens. Therefore, you have psi arrow chi, which is the same as phi star. In the case when chi has been assigned 1, then chi star is the same as chi, phi is been assigned 1, and therefore, phi star is the same as phi. So, phi star is the same as psi arrow chi. So, we have this proof tree proving chi by the induction hypothesis, and then we can use that proof tree starting with the axiom k, where you have chi arrow psi arrow chi, and you have proved chi here in this proof tree, and therefore, you have psi arrow chi, which is the same as phi star. Yeah. the last subcase when psi has been assigned 1 and chi has been assigned 0, clearly phi is not true, since phi is of the form psi arrow chi, right. So, which means that firstly psi star is the same as psi, chi star is not chi, and phi star is not of psi arrow chi. So, we have these proof trees T 1 and T 2 by the induction hypothesis, which from the same assumptions gamma prove respectively psi star, which is psi, and chi star, which is not chi. And now what we do is we have this derived rule here which says x arrow not y arrow not of x arrow y, right. If you proved, so you can use this derived rule along with T 1 which proves psi, apply modus ponens to get not chi arrow not of psi arrow chi, and of course, you have by the induction hypothesis this proof tree T 2 with the conclusion not chi. So, you can again apply the modus ponens rule to get not of psi arrow chi, which is the same as phi star, right. Okay. So, those exercises were actually important in order to show that you can simulate every row of a truth table by a proof, by a deduction from the assumptions, which are the truth values essentially of the atoms of the truth table, right. So, now the actual completeness theorem has to show that every tautology in L naught is a formal theorem of the system H naught. And though I thought it was, though I initially felt it was sort of like obvious, if you have simulated the entire truth table, then you have intuitively clearly captured all the semantics. So, that intuition is fine, but the formal proof of this theorem still requires the fact that you are not allowed to have any assumptions, right. You are talking about every assumption, the truth table has assumptions, right. The atoms, the truth assignments to the atoms are still assumptions in every proof. So, is it clear that from there you can actually get down to proving every tautology, and that step is not as trivial as I originally thought it was. And this is and it is also a very beautiful proof, as you can see. So, we will go through this proof, right. So, what we do have is that every row of the truth table can be simulated by a proof, where the truth values of the atoms form the assumptions of that proof, right. So, what I will do is, so we will encode each row of the truth table, which is standard, by a bit string of, if we are talking about k atoms, then each row of the truth table has essentially k columns, one corresponding to each atom. Take the k atoms in the order p 1 to p k and take the truth assignment in that row as essentially a k length bit string, right. So, now what we are saying is, so the truth table lemma essentially says that for every such k length bit string S k, I have a proof tree. Oh, and we have to prove that every tautology is a formal theorem. So, assume phi is a tautology, which means the truth table assigns the truth value true to in all rows of the truth table to phi. So, phi star in this case by the truth table lemma is just phi itself. So, now what this means is that corresponding to each row of the truth table, I have a proof tree T S k, where the assumptions are gamma S k. So, I am using the same encoding to specify what is the truth assignment to each of the atoms. With those atoms, I can prove phi. I mean, that is this. So, this is given from the truth table lemma. Okay. So, for each, now what we are going to prove is that you take any bit string S j where j is of length less than or equal to k, we are going to construct the proof tree T S j such that gamma S j proves phi. Okay. So, in the case when j is equal to k, of course, we already have these proof trees, but what we are going to do is we are going to systematically contract the assumptions till j becomes 0. Okay. When j becomes 0, essentially you have got a gamma S0, S0 is just the empty string, that is gamma epsilon, and essentially that is an empty set of assumptions. Otherwise, Sj for j less than or equal to k essentially gives you the truth assignment for each of the atoms P1 to Pj, and assuming that you have already removed the atoms Pj plus 1 to Pk, right. So, what so there are 2 raised to k rows on the truth table, and we have 2 raised to k different proof trees, one for each string Sk. There are 2 raised to k strings, bit strings of length k, right. So, what we are going to do is we are going to contract these bit strings till you come to the empty bit string, right. Okay. So, this is what. So, in order to do that, consider 2 bit strings which differ only in the last bit, in the rightmost bit. Okay. So, assume that so we have already got T S k, right, for all of the case. So, you take essentially, so starting from any proof tree T S j, you take S j minus 1 0 and S j minus 1 1. Okay. So, you have got proof trees T S j minus 1 0 and T S j minus 1 1, which prove from the assumptions gamma S j minus 1 1 it proves phi, and from gamma S j minus 1 0 it proves phi, right. So, this is a j length bit string, this is also a j length bit string, where S j minus 1 is a j minus 1 length bit string, and then you have a 1 or 0. So, essentially we pairwise we choose the 2 bit strings which are identical, who have identical j minus 1 prefixes, but differ only in the jth bit, right. Okay. So, what we then what we are going to construct is a proof tree T S j minus 1 from these 2 proof trees. Okay. So, this is very simple. So, this is how we are going to go about it. So, you take T S j minus 1 1, which proves from gamma S j minus 1 it proves phi, and you apply essentially the deduction theorem, so that you move the jth assumption to the right. So, when you move the jth assumption to the right, you get P j arrow phi, right. In the case of 1 you get P j arrow phi, in the case of 0 you get not P j arrow phi, right. And then we have this exercise of proof by cases, right, which shows that, which says that x arrow y and not x arrow y implies y, essentially that is what it says. So, this is a proof by cases, and so we essentially apply this proof by cases, right. So, when you apply this proof by cases, and for these 2 conclusions P j arrow phi and not P j arrow phi, you get that gamma S j minus 1 proves phi, right. So, what we have done is we started with 2 raised to k different proof trees, and we halved it by taking proof trees pairwise and creating proof trees 2 raised to k minus 1 proof trees with assumptions only from P 1 to P k minus 1. And this procedure of removing the rightmost assumption is very general, it is absolutely general. So, you can do this systematically one by one. So, we start with 2 raised to k proof trees, halve it down to 2 raised to k minus 1 by removing the assumption P k and not P k. Then you remove the assumption p k minus 1 and not p k minus 1 and so on, and till you will actually obtain this a single monolithic proof tree, right. And this procedure is absolutely general, and this proof by cases works as generally, right. So, this one monolithic proof tree, essentially gamma epsilon is empty, and therefore, you have proved that starting with the assumption phi is a tautology, it can actually be proven, right. So, this is how this proof goes, and this proof cannot be replicated the moment you have a system where the semantics is infinitary, right, and that is precisely what is going to happen when we do first order logic, right. So, this which means when we come to first order logic, there are certain things that we will not have any access to. One is the notion of a truth table, or at least a finite truth table. Or any logical notion of a truth table there will probably be infinitary, depending on the model that you are looking at, depending on what you are trying to axiomatize. Secondly, there is so which means that this proof is actually unique to this construction, and therefore, this proof will not, such a proof cannot be extended easily to first order logic or anything which has an infinitary semantical nature, which might generate infinite graphs or infinite trees and so on, so right. And you can see that this proof is also very different from the proof of completeness that we used for the tableau system, right, because there the question was not really of validity, but of unsatisfiability or satisfiability, right. And so, you have different kinds of proofs, and it is a good idea to actually look at. So, it is a good idea to look at various different kinds of proofs, whereas the tableau method of completeness proof might actually be applicable even to other systems which are infinitary in nature, but this kind of a proof will not be applicable there, right. So, there is actually one more concept which I have not done, but which I will mention, but I will not proceed further with it. And that is a very important concept, but I do not think we have either the time or the wherewithal to actually deal with it, and that is the independence of axioms. So, we had several important concepts in a logic. So, we of course, we have already dealt with 3 important concepts. One is of course, this I mean besides soundness, completeness, compactness. So, these were the 3 important concepts. There is a 4th important concept called independence, and that independence has to do with the question of. So, we have this notion of derived rules and derived operators. We also had this notion of adequacy and functional completeness, right. So, our functional completeness essentially said that any operator that you might define in propositional logic can be expressed in terms of whatever the operators of L naught. Actually, it is enough to just have, it is adequate to just have the operators arrow and naught, right. So, in that sense, the operators, any operator that you might define for propositional logic is not functionally independent of the operators arrow and not. Okay. This a similar and analogous notion is that of independence of axioms and inference rules. Right. So, one important thing that therefore which needs to be shown, especially in a minimal system, the Hilbert system was supposed to be a minimal system, is that the two concepts, I mean the axiom schemas of the Hilbert system are mutually independent. It is not possible to take any subset of those axiom schemas and inference rules and prove the rest as in a derived fashion. This independence is actually a fairly hard concept to prove, but it is an important concept. For example, it is not a concept that is easily applicable to something like natural reduction, which is not meant to be a minimal system. But if you take a minimal system, then you actually have to prove the independence of the axioms, and the proofs of independence are in general not very easy. So, I will not actually go into them, but independence is an important concept from the point of view of a logical theory for other reasons. So, yesterday I took the example of the parallel postulate, right. So, what are we saying now? I can remove Euclid's parallel postulate and put in another parallel postulate which says that there are no parallel lines basically, okay, and still get a consistent geometrical theory. I can still have a sound geometrical theory. So, in that sense, the parallel postulate is sort of independent of other axioms of Euclid, right. And this independence notion also comes up in when you do something like axiomatic set theory, right. So, one of the most brilliant proofs of independence was this. So, I do not know how much of axiomatic set theory you know. So, it is possible to take treat set theory as an axiomatic theory very much like the way we have defined within the domain of first order logic, okay. So, which we have not yet done, okay. And one of the important things about axiomatic set theory is this notion of the axiom of choice, which actually you have probably seen in a different fashion, because the axiom of choice is actually equivalent to two other things. One is Zorn's lemma, and the other is the well ordering theorem, right. Yeah. So, and actually in any kind of in a large number of proofs we use the notion of a well ordering, the fact that there are no infinite descending chains, right. And this, so what for a long time it was assumed that the axiom of choice which essentially is required for which is required for any kind of proof that you have only a finite sequence, or it is always possible to construct from an infinite set some finite from some total ordering and so on and so forth. All those things require this notion, either the axiom of choice, or they require a form of well ordering, or they require Zorn's lemma. But what Paul Cohen showed in the 60s, well after axiomatic set theory was well established, was that this axiom of choice was actually independent of the other axioms of set theory. So, which means it is possible to remove the axiom of choice and have a completely separate set of set theory, a separate axiom system for set theory, a non-standard set theory, in which the axiom of choice may not be applicable. The moment axiom of choice may not be applicable, it also means you may not use any kinds of well orderings, you cannot use Zorn's lemma and so on and so forth, right. And in that sense, you still have a the axioms of set theory still allow enough leeway to add some other axiom instead of the axiom of choice, because the axiom of choice itself is independent of that, right. But this concept of independence otherwise in a first course on logic is actually quite hard to understand, though it has come up with some phenomenally interesting results on formal theories. So, I will not, so this is a concept that I will not touch on, we will proceed straight to first order logic. Yeah. And so, today I will not, it is probably too late to start that, right. I think we will stop here today.